Okay, so let's go with the second part of this little project. We have spent about 45 minutes writing this model that does the actual data, and then that adds on top of that an observation process that is destroying the actual data and giving us a version that is biased, in which observations are missing. What we want to do now is just to take a few steps back, is get that thing that we have here. I'm going to put it here again. And it's a list of observation from 15 years. And we would like to know what the possible values of the colonization and extinction rates are. So that's where we go for an approximate Bayesian computation approach. Approximate Bayesian computation works when you don't necessarily know the mathematical expression of the solution, or more precisely, you don't know the mathematical expression of the likelihood of the model given the data that you have, which for this model is not necessarily true, but it's still a good illustration of the process. And so instead, what we can do is make the data and the model speak the same language. And the language that the data and the model are going to speak is the language of summary statistics. Or because we don't want to reproduce that exact time series. And the reason why we don't want to reproduce that exact time series is that there is possibly a lot of different parameters that could give us this time series, but there are also a lot of different time series that could be given by the same set of parameters. And so we want to find a model that, when given the right parameters, is going to create a time series that looks like the one we have here. And one of the core difficulties of using ABC is to define what looks like mean. There's a whole body of theory about about the sufficiency of summary statistics. And that's something that we're going to ignore for this exercise because we have a limited amount of things we can do. What we're going to do is say that a time series here is defined by two things. The first thing is, what is the average occupancy? So we can calculate the average occupancy of that. We're going to need to add statistics, by the way. Yep. Okay. So let's go with summary statistics. We have a function, occupancy, that's going to take a time series, which is a vector of Boolean value once again, and it's going to be the mean of the time series. So if we look at the occupancy of the island, it's 0.53. That is the occupancy that we have observed, the occupancy that we infer based on the data sets that we have. So that's cool. The second summary statistics we can use, there's 2 or 3 different we could use, but we are going to look at the rate of transitions. So how frequently do we have a transition, which is to say the value at time 1 and the value at time 2 are not the same. So we are going to create a function called transition rate. And, we could loop through the entire thing and say it's time 1 and time 2 equal or different, but we could also say, let's have a quick look. We could do island 1 to end minus 1, and we could do island 2 to end, right? And that's like we're checking the entire time series and we're shifting it a little bit. And so we could do island at times t, is it equal to island at times t plus 1? That's going to give us 14 things. And if we want to have the rate of transition, we want to know, well, what we want to know is when it's actually different, right? And so the average times where it's different is the mean. And so there's, on average, a 35% chance that the system is going to change state between one time and the other. So we could just rewrite that as a quick one-liner called transition rate, which again is a time series, which is a vector of Boolean value, and it is the mean of, that is a long line, but that's fine. Okay. So occupancy transition rate. What we're doing is that we're going to say, well, we have 15 points here. But if we want to simulate our model for thousands of years, we could still reduce that to what is the occupancy and what is the transition rate. And so that's one way of bringing the empirical data we have to the simulated data into the same space. So let's have a quick look. Let's do observed, it's called observed dynamics over 1,000 years. Come on, run it. And then we can look at the occupancy, which is 0.49, and we could look at the transition rate, which is 0.28. So what we know is that the occupancy of the time series, the actual time series is about 0.54, the transition rate is 0.35, whatever. And then for a simulated time series of 1,000 years, we get these two values. Now the question is, are these two values a good representation of the empirical data set? Yes or no? And so in order to do that, what we need to do is to figure out what the distance is, not between the model and the data, but between the summary statistics of the model output and the summary statistics of the empirical data that we have. Because we could change the model, we could get different data, but they're all going to converge to speak the same language of what defines a time series is occupancy and transition rate. So let's write a little function called distance. And the distance is going to take some data, which is a vector of Boolean values, and it's going to take some simulation, which is also a vector of Boolean values. They don't even need to be of the same length, right? And we are going to say x. The value of x is going to be occupancy of data and transition rate of data. And then y is going to be occupancy of simulation, transition rate of simulation. In order to get the distance, we are going to do the simplest things we can. So let's just, we are going to do x minus y squared, take the sum, and return the square root. Or in other words, we are going to assume that we are taking the Euclidean distance between the summary statistics of the data and the summary statistics of the simulation. There's other distances we could use. There are, in many instances, there are distances that are more appropriate. The assumption we can do here is that because everything is a rate of occupancy or rate of transition, it's going to be between 0 and 1, and so it's expressed on the same scale, and so we're fine. So let's run this function here and have a little test. We're going to check the distance between the island, which is the data, and observe dynamics for 1,000 years. And that's telling us, it's telling us that I should pay attention when I write code. Yeah, that is telling us that the distance is 0.10. So what's important to keep in mind is that when we are going to run this model, because it is a stochastic model, there is going to be a change in the result. And so there's going to be a distribution, even with the same parameter value. We could do that for, that's probably a repeat function, like I'm quite sure, but anyway. We could do that for 1,000 different simulations and plot the distance. And we say, well, the distance could be anywhere in this interval. The point of ABC is not to say, well, it can be anywhere in this interval. So we're just going to draw one sample and say that is going to be the sort of distance that we could get for this one sample. And we're going to do that a lot of time. Before we do that, I'd like to take one step back and say, and discuss a choice that we've made. And we've made a choice of summarizing the data and the simulation by only two values, the occupancy and the rate of transition. That's line 63 and 64. We could do a lot more things. We could do what is the average duration at which the island remains empty, or what is the average duration at which the island remains occupied? What is the rate of transition from false to true? What is the rate of transition from true to false? We can divide this time series in an overwhelming number of ways. But the point is, when we do that, we are increasing what we call the dimensionality of the problem. For the moment, our problem has two dimensions. The dimension number one is occupancy. Dimension number two is the rate of transition. And one thing that is fairly well described when you're trying to fit data to a model to anything is something called the curse of dimensionality. And it has to do with the fact that when you increase the number of things that you compare, you have a higher chance, you expect actually the distance to increase. And so what you're expecting is that the performance of your model is going to get lower and lower because there's just more possibility by chance that you're going to miss one of these targets. So there's always a balance where you want to find summary statistics that are going to find the signal in the data. But you don't want to use that many summary statistics that you're going to have all of your distances converge to basically infinity, and so your performance converging to zero. That is what you want to avoid. In this specific case, we would probably be fine with decomposing the rate of transition in two components, but as you'll see, we'll get some respectable results with only these two functions. So the choice of summary statistics is literally going to make or break the success of the ABC process. The choice of the distance function is as well, but the summary statistics is particularly important. If you want to convince yourself that, and I know it's a little bit counterintuitive, if you want to convince yourself that the curse of dimensionality exists, one of my favorite ways to get an intuition about that is to imagine points on a line. If you have points on a line, there's a given distance between them. But then if you shift your point of view to realize that the line was actually a plane, you gain one dimension, but you keep the same number of points. And so suddenly, if you look at them this way, or the distance between them is going to increase. And then if you shift again some more to realize that, no, actually there was a cube, you still have the same number of points, but the distance between them is going to increase some more. And so you are going to say, well, these points are less similar the more dimension you add. And so if you want to maintain the same ability to get the same close distances between things, you need to add a lot more points when you increase the number of dimensions. And so that's I think that's an interesting consideration to have when you want to compare things based on summary statistics. So the next thing we need to do, there's 2 steps that are left to do before we have a fully functional ABC. We've done most of the work, actually. The next step is to say, when do we say this sample is good enough? And what we mean by a sample is a combination of parameters. So here a sample is going to be 3 values: the rate of colonization, the rate of extinction, and the rate of making a correct observation. There's 3 points. That's going to be a sample. The sample will go into a model. The model will create a simulated data set. The data set will go into summary statistics, which will go into the distance function that will give it a score. And a good sample should have a distance that is close to 0. It's never going to be quite 0, because it's almost never going to be perfect, but it's going to be close. And so if we say, well, I'm going to say a sample is good if the distance is, let's say, lower than 0.2 here, then we're going to say, what about like 95% of the samples are good? So that's not very discriminant. If we say, well, I want something that's below 0.05, it's probably going to be a little bit better, but we're going to be doing a lot more simulation to get a large enough sample size, and that's only for one parameter value. But one of the decisions that we need to make when we are doing approximate Bayesian computation is to set a threshold, because the thing we're going to do here is called rejection sampling. And in rejection sampling, we are going to try a lot of things, and we're going to reject all of the samples that give a distance that is higher than a threshold that we want. There are some little heuristics that we can use to estimate a right sample. We could do like nested ABC. There's a lot of different things we could do. We're just going to check this figure and eyeball it and say, well, 0.05 is like it's doable. And the model is quick to run as well. So we could do a lot of them, and we could be a little strict with how much we want to follow the actual data set. So we're going to set a threshold that is 0.05. So the last thing we need to do, that's like what is the cutoff to reject a sample, is to define the distribution of the parameter values. So what are the parameters? And that is why this is a Bayesian technique, is that we are going to set a distribution of the parameters that is a prior distribution, that is the expectation of what this parameter should look like. And what we're going to do is, I was just eyeballing it during the break. We're going to say that the distribution of the extinction rate is a beta distribution with parameter 2 and 5, I'll say. And let's plot that. Let's plot D of E. So the beta distribution is as support in 0, 1. So that's good because it's a rate. We like that. And this one with 2 and 5, it's going to say that we expect that on average there's a 25% extinction rate. And it shouldn't be much more than 0.75 anyway. We are going to say that for the rate of colonization, we are going to do beta 2, 3. Let me do that. It's going to be, temp bright default frame equal box. Plot DE and lab equal extinction. So that's going to be our extinction rate, and then we can do DC, which is the rate of colonization. Of course, it's plot bang. Okay, so we have why do I use the beta? Because it has support in 0.1, because I like it for some reason. It has a few other desirable properties that we're not going to go into. But what we see here is that we have a rate of extinction that is lower on average than the rate of colonization. So we expect that the island is going to keep being occupied. And it's probably widely unrealistic, right? But the point is, there's a subset of this distribution where we should have the correct value that are going to give our time series. The next one we need to do is that we need to find a way to express the errors that we're making when we're measuring something. And for this one, we're going to use an inverse gamma distribution. The inverse gamma distribution is interesting because it's not supported it's supported in 0 to infinity. I think, let me check. I'm sure there is. Yeah, it supports the M. It's 0. And question in the chat: is there a benefit to 2 separate beta distribution instead of 2 Dirichlet? Yeah, no. It's literally up to you. But so the beta distribution is a one-dimensional specific case of the Dirichlet distribution. We could definitely do either of this thing. There's no strong rationale either way. The one case would be if you knew that we're just assuming that both parameters come from a beta distribution, which is not always the case. And in that case, yeah, it could definitely be a 2D Dirichlet. Okay, so let's plot DM. So that is the inverse gamma distribution. I'm only picking this one not because I think it's the best for what we're trying to do, but because I want to show you a quick functionality of the distribution package, which is we have a distribution that can go from 0 to infinity, but we know it's a rate, and so we're not interested in values that are larger than 1, so we are going to put that into a call to a function, which is called truncated. And what that is going to do is ensure that we have a distribution that is supported in 0, 1. And if we plot dm, we know that it's going to be going into 0, 1. So the distribution package in Julia has a lot of really, really powerful way to deal with distribution. And so we are going to use that for our little sampler. So one of the things we can do now is we can extract a value from our thing. So we could do rand dm, and that is giving us one sample that we can use for the simulations. So the point here is we're going to draw a lot of samples. And every time this sample gives a simulation that has a distance that is above the threshold, we're going to reject it. Every time this sample has a distance that is below the threshold, we're going to keep it. And there's a number of ways to do that. We could just say, well, we're going to run 10,000 simulations and keep the one that works. Or we're going to run as many simulations as we need to get 1,000 different samples in the end, which is probably not enough, but let's start with that. Or we're going to pre-generate all of the values and then do filtering. There's a ton of different ways to approach this problem. What we're going to do in order to be somewhat efficient with memory allocation is we're going to say we want 100 samples just to start. So allocate a space for the retained samples. So it is going to be a matrix. All of them are floating points, and it is going to have 3, and then 100. So every sample is going to be a column, and one row is going to be all of the samples for all of the values for this parameter across the samples that we do. We are going to start with the number of successes, which is going to be 0. For the moment, we have not had a single success because we have not run a single simulation yet. So that's normal. And what we want to do is, while successes is less than size params 2, we are going to run the simulation. So what are the simulation we're running? We are running, we are getting a value for M, we are getting a value for C, and we are getting a value for E. That's our candidate sample. When we have this candidate sample, we can create the time series. So our time series is going to be observed dynamics. We're going to do 1,000 time steps, and it's M equal Tm, C equal Tc. There's a better way to do that, but it's fine. Equal to E. And then the score is going to be the distance between the data and the time series. So every time we do that, we are going to be recalculating the same summary statistics on the data, which is obviously not efficient, but given the very, very low complexity of the problem we're having here, it's fine. So here's the score, and then what we want to do is, if the score is lower than the threshold, we are going to, successes, we're going to add 1 to the success. And what we are going to do is say that params at the line which corresponds to the number of successes is going to be equal to, let's say, M, C, and E. And we're going to make a little info message. They got success is good samples. Okay. That should, oh, data not defined. Yeah, that was fast. It's not data, it's island. Okay. So we got 100 different samples. The question I'm interested in at the moment is, out of how many? Because if we're accepting every sample that we get, it's not really efficient. We're not learning anything. We just have a distance that is so large that it's not really making much of a difference compared to just like doing random simulations. So we're going to do trials equals zeros, and we're going to do trials increase at every time step. Let's rerun the thing. I still get 100 samples, but what we can do is look at the number of trials. So we have done 1,600 trials. So the rate of acceptance is 100 over trials. So we're accepting about 6% of the samples. So that's, it's sort of our call to say, well, is it good or is it not good? We could get back to the data and have a look to see if that describes them correctly or not. But what that's telling me that maybe, you know, we could probably get a better result if we decrease that a little bit. So we're going to say 0.03. And then our rate of acceptance is 100 over trials. and we get a 2% rate of acceptance. Depending on the difficulty of the process that you want to fit, that can be good or that can be bad. And in some instances, if you want to stick very, very closely to the empirical data, you might want to have a 1 out of 1,000 rate of acceptance or something like that. That being said, there's a strong argument that if you decrease the threshold too much, you risk overfitting the model. And so it's good to give yourself a little bit of stochasticity in there, a little bit of leeway around what is an optimal parameter, because that gives you a little bit more generality. And also the model that we're using is not correct. It's not an adequate representation of reality. It's just a model that looks like similar. So there's no point in trying to get a like 1 out of 1,000,000 rate of acceptance. If it's like 95%, your threshold is too high. But if it's like 10 to the minus 5, your threshold is probably way too low. Okay, let's have a look. That's what we wanted to do, right? We wanted to compare what is the plot of the C. So that's our original estimate for the rate of colonization. And where did I put DC? Let me look at params. It's the second one. It's the empty. We could plot the density of it's going to be params 2, right? Yeah. Okay. 0, 1. So this is the blue. Okay, let me just label this axis correctly. Lab equal C is colonization rate. Prior, and lab is colonization, but that is a posterior distribution. And so what we see here is that we started from a distribution that was a beta with some specific parameters, and then the distribution that we have in the end is something that is different. So we have corrected the distribution in a sense towards something that is a bit more probably fitting the data a little better. So what I want to do? Yeah, one thing that we should do, because a density gives you this idea that it's actually really smooth and all that, but yeah, that's what I thought. I made a mistake. Yeah, it's more like it. Okay. Yeah. So the density gives you this idea that it's more like it's really smooth, and what we want to do is look at the histogram. And the histogram here, it says, well, that's actually not too bad, but we can see that there is a range of variation on the exact value of the colonization parameter. So that's also a useful visualization, I would say, for checking if the threshold is high enough or low enough. That maybe we want something that is a bit more defined. Let's have a look for the other values. So extinction, that was the E, and extinction is the third. That was the prior, that is the posterior, and that is the correct axis. It's cool. And let's finally do the M, which is the measurement parameter. And that is the first one. So the measurement parameter, by chance, we got it like quite right. Let's try and make a little experiment by decreasing the threshold some more to 0.15, I would say, and run this thing. And it took us 21,000 trials to get 100 samples. So, but let's have a look at, is it changing the distribution? Not by a lot. We have something that is a bit more defined, but it's not necessarily something that is entirely changing our understanding of the model. So one thing I like to do is like plot the actual posterior distribution, because that's what we want. So that's colonization is here, extension is here, and the measurement error is here. Okay, and like as you can see, this is different from what we had as a prior that I forgot to do, but I can do that quickly. Let's do that. Let's put them side by side, just because I think visualization is definitely really important when we try to understand what's up with the model. Plots do we're going to add that here. You'll see why in a moment. Okay, so that's the priors, and that's the posterior pos. Anyway, that's how to pos, and we could plot both of them together. Cool. Okay. Yeah. And so what we can see here is that, even though the colonization and, the extinction and measurement priors were not necessarily, we did not miss them by that much. The estimates that we've made were somewhat realistic. We severely underestimated the colonization rate in the sample that we had at the beginning. So that's cool. We're done, by the way. This is how we get to fit the this problem using ABC, but we're not quite done, because what we've reproduced here is something that is that can generate observed data. But what we are interested in is like the real life biology. So what if we remove the extinction process, right? What if we were to look at time series, but for which we can assume that there is no observation error? So how do we do that? We can do time series with no observation error. One solution is to set the C parameter in observed dynamics to 0, but that's not what we want to do. What we want to do is call the island dynamics function. I could do that for 1,000 years, and we're going to say C equal, let's say params, what is colonization? 2, 1. And E equal params 3, 1. So if we do that, we could plot it. I don't care. Yeah, not really the best thing we can do, but anyway, we can generate a time series that is different in that it has the actual occupancy of the island. Let me show you why that's important. But what if we do? We look at the occupancy of. No, we're going to do things slightly differently. Sorry. We are going to say for I in. Here's what we're going to do. We are going to look at the occupancy of this for I in size params 2. That's going to be, sorry, here it's I and here it's I. So we're just going to take the samples that we got and get a distribution of occupancy, right? And so we could pass them to an histogram. And that is the actual occupancy that we would expect from the island. And then on top of that, we could add the occupancy that we measured, and lab equal. And so what's really nice here is that the red line is the measurement, it's the empirical data, but the blue histogram is what we expect the distribution to be in the situation where there would be no observation error. So if we manage to correct the bias, that is removing observation, we would expect that the occupancy of the island is actually much higher by about like 20%, 15% than what we have actually measured. We could do the same thing with, let's put that to density and do an x-axis 0, 1. Yep. And that, yeah. And we could do the same thing with the transition rate here. And if we do the same thing with the transition rate, then we can say that we are overestimating the rate of change, so the rate at which a species is going extinct or reappearing on the island by a substantial amount, which I think is an interesting illustration of what ABC can do. So that in this specific example, what we've used it for is to infer the biological parameters, but also infer the observation process that is leading to the dataset being not quite as good as it should have. Just to get back to something that is very important, is that we can also start to get a sense of what are the association between the parameters. So parameters relationship. So what if we do a scatter plot of params 2, which is colonization, and param 3, which is extinction. We're seeing this sort of things. What we're seeing is that there are multiple scenarios for this island here, right? And so we could have, we could observe a time series that looks realistic with a, sorry, the x-axis is going to be colonization, and it's going to go from 0 to 1. And y-axis is going to be extinction. And go from 0 to 1 as well. And there's no need for a label. Okay, so what we have here is the fact that, sure, if we look at on average, it's going to be here, but there is also a relationship between the parameters that we're inferring, right? And so there can be a couple different reasons for that. It can be because of actual biology, like an island that has high colonization, high extinction, or low colonization, low extinction might as well have the same occupancy because the same processes, they're just happening at different times. Maybe it's because the summary statistics that we use were not sufficient. Maybe if we had decomposed the problem into a number of, like probability of a colonization event, so probability of an extinction event, we would have gotten something that was maybe better, or at least not introducing this sort of dependency between the parameters here. So there's a number of reasons for which it's important. But the thing is, when we are making simulation of the dynamics on the island using samples that are drawn from the posterior distributions, we are respecting the structure. So we're not taking colonization from sample 2 and extinction from sample 300. We're taking both of them. Like this pair of points is a sample that makes sense. And so that's an interesting visualization to make. Just make sure to understand what the relationship between the parameters that you are manipulating are exactly. So we have we've done quite a lot of work here because we know a code that can go from an observed time series, can recreate the time series, add on top of that an observation process. Then we can summarize it using two statistics, measure the distance between the model and the empirical data, and use this as part of a rejection sampling to get a better approximation of what the parameters will be. So that is the end of, that's where ABC can end. We can decide to say, okay, we're done here. We have an estimate. We have a probability distribution for the parameters. Problem solved. And that's true in a sense. We're going to take a break for 15 minutes, and so we're going to start at 11:15, and then we're going to spend some time using this as an excuse, mostly to talk about parallel computing and mostly using multiple threads to run more simulation at the same times. As you've noticed, the model is really fast, but we're going to see if we can get more work done in a shorter amount of time, and also what are some common pitfalls that we can run into with parallel computing. So I will see you in 15 minutes.